Welcome to Chapter 3, Drug Discovery MI Implementation with Python. This is a hands-on chapter where you'll learn practical molecular design through 30 executable code examples. We'll cover RDKit basics, CH-EMBL data acquisition, QSAR model building, ADMET prediction, and even graph neural networks. Before we start coding, let's set up our environment. The key libraries we need are RDKit for cheminformatics, the CH-EMBL web resource client package for database access, scikit-learn for general machine learning, lightgbm for gradient boosting, and pandas, numpy, matplotlib, and seaborn for data processing and visualization. You have 3 installation options. Option 1 is Anaconda, recommended for beginners because it handles dependencies automatically and RDKit installation is easy. Option 2 is Venv, Python's standard virtual environment, which is more lightweight. Option 3 is Google Colab, which requires no installation at all. You just need a browser and can use free GPU. For Anaconda installation, create a virtual environment with Conda Create, activate it, then install RDKit with Conda from the CondaForge channel. Install other libraries with Conda and pip. Verify the installation by importing RDKit in Python. This setup gives you a complete drug discovery environment. Now let's dive into RDKit basics with example 1, creating a molecular object from a SMILES string. First import chem from RDKit, then define your SMILES string. Convert it to a molecular object with chem, mol from SMILES. You can then get basic information, molecular formula, atom count, and bond count. One thing to watch, by default RDKit counts only heavy atoms, so aspirin reports 13, not 21. Call add HS first if you need hydrogens included. Important, mol from SMILES returns none for invalid SMILES, so always add error handling. Create a safe mol from SMILES function that checks if the result is none and prints a warning. This prevents crashes when processing large datasets where some SMILES might be malformed. Example 2 covers molecular visualization. Use draw mols to grid image to display multiple molecules in a grid. You can specify molecules per row, image size, and legends. This is essential for visually inspecting your compounds. The output can be saved as PNG or displayed directly in Jupyter notebooks. Example 3 demonstrates calculating physicochemical properties. Import descriptors from RDKit and calculate. Mol WT for molecular weight, mol log P for lipophilicity, TPSA for polar surface area, num-H donors and num-H acceptors for hydrogen bonding, and num-rotatable bonds for flexibility. Store results in a pandas data frame for easy analysis. Example 4 implements Lipinski's rule of 5, the drug likeness filter. Create a function that calculates molecular weight, log P, hydrogen bond donors, and hydrogen bond acceptors, then checks if each is within the established limits. Return both the values and pass fail status for each criterion. This is a fundamental filter in drug discovery. Example 5 shows how to generate ECFP molecular fingerprints. Call the Morgan fingerprint helper, get Morgan fingerprint as bit vect. In the all-chem module, choosing the radius that matches the fingerprint you want, where radius 2 gives ECFP4. Then convert the result to a NumPy array with the convert to NumPy array helper in data structs. You'll get a binary vector of typically 2048 bits that encodes the molecular structure. Example 6 calculates Tanimoto similarity between molecules. Generate fingerprints for both molecules, then use data structs, Tanimoto similarity to compare them. Remember the thresholds. Very high values indicate the same compound class, high values indicate similar with possible similar activity, and low values mean different molecules. This is the foundation of similarity-based virtual screening. Example 7 demonstrates substructure searching using SMARTS patterns. SMARTS is a language for specifying molecular patterns. Create a pattern for features like a benzene ring, then use mol. Has substruct match to check if a molecule contains it, or mol, get substruct matches to find all occurrences. Essential for filtering compound libraries. Example 8 covers three-dimensional structure generation. Add hydrogens with chem, add HS, then call all chem. Embed multiple comps with the ETKDG version 3 parameters to generate 10 conformers at once. Optimize each conformer with all chem.uff optimize molecule using the UFF force field, calculate its energy, and keep the lowest energy conformer. You can save the result as a MOL file with chem. Mol-to-mol file for use in docking or visualization software. Example 9 shows batch calculation of every descriptor RD kit provides. Loop over descriptors desk list, fetch each descriptor function by name, and evaluate it on the molecule. That gives you over 200 descriptors in one pass. For aspirin, print the key ones: molecular weight, log P, TPSA, hydrogen bond donors and acceptors, rotatable bonds, and ring counts. Then save the complete result as a one-row data frame to a CSV file. Example 10 covers reading and writing SDF files, which store multiple molecules with properties. Use chem, SDMol supplier to read SDF files, iterating through molecules and extracting properties with mol, getprop. For writing, use chem, SD writer to create a new SDF file. This format is standard for sharing compound libraries. Now let's move to CH-EMBL data acquisition. CH-EMBL is the premier bioactivity database with millions of compounds. Example 11 shows how to search for targets. Import the new client object from the CH-EMBL web resource client package, then call filter on its target endpoint to search by name or target type. For EGFR, you'd search for epidermal growth factor receptor to get its CH-EMBL ID. Example 12 retrieves bioactivity data for a target. Use activity filter with the target's CH-EMBL ID. Filter by standard type equals IC50 and add appropriate activity thresholds to get potent compounds. Convert results to a data frame for analysis. This gives you curated activity data for QSAR modeling. Example 13 preprocesses CH-EMBL data for machine learning. Remove rows with missing smiles or activity values. Convert IC50 to PIC50 by taking minus log base 10 of the concentration in moles per liter. CH-EMBL reports values in nanomolar, so divide by 1,000,000,000 first. 100 nanomolar is 10 to the minus 7 molar, which gives a PIC50 of 7. In practice, the example takes the PCH-EMBL value CH-EMBL already provides, then cleans in 4 steps. Drop duplicate CH-EMBL IDs so each compound appears once. Reject SMILES that RD-Kit cannot parse, keep molecular weight at or below 600, and keep PIC50 between 6 and 12. This data cleaning is crucial for model quality. Example 14 builds a complete dataset pipeline as a reusable function. You handed a target CH-EMBL ID that you already know. The search step was example 11. It retrieves IC50 records with PCH-EMBL value greater than or equal to 5, skips entries with missing activity or smiles that RD-Kit cannot parse, and turns each valid molecule into a 2048-bit EC-FP fingerprint. It returns 3 things: the fingerprint matrix X, the PIC50 vector Y, and the SMILES list. This creates a ready-to-use dataset for training machine learning models. Example 15 is data preprocessing and cleaning. First, remove outliers with the interquartile range rule. Compute the first and third quartiles of PIC50 and drop anything more than 1.5 times the interquartile range outside them. Then split the remaining data 80-20 into training and test sets with a fixed random seed. Plot the PIC50 distribution for both sets as a histogram and a box plot to confirm they look alike, and save the 4 arrays for the modeling examples that follow. Now we build QSAR models. Example 16 simply loads the 80-20 split that example 15 already produced, the 4 arrays XTrain, XTest, Y-train, and Y-test, and prints their shapes so you can confirm the fingerprint width and the sample counts. There is no separate validation set here. Hyperparameter tuning comes later, through cross-validation on the training set. Holding out a test set this way prevents overfitting and gives honest performance estimates. Examples 17 and 18 both train random forests. Example 17 is a classifier. Label a compound active when its PIC50 is 7.0 or above, then fit random forest classifier with 100 trees, max depth 20, and min samples leaf 5, and score it with a classification report, and ROCAUC example 18 is the regression counterpart, random forest regressor. Also with 100 trees, predicting PIC50 directly. Random forest is a solid baseline that handles high-dimensional molecular fingerprints well. Example 19 implements support vector regression. Use SVR from Sklern, SVM with an RBF kernel. Support vector methods work well for smaller datasets up to 10,000 compounds. Scale features first using standard scaler because SVR is sensitive to feature scales. This often achieves similar accuracy to random forest. Example 20 builds a deep neural network with Keras and TensorFlow. Standardize the fingerprints, then stack dense layers of 512, 256, 128, and 64 units with dropout after the first 3, and a single output unit for regression. Use RayLU activation and the Atom optimizer with mean squared error loss. Neural networks need more data, ideally 10,000 or more samples, but can capture complex nonlinear relationships in molecular data. Example 21 shows feature importance analysis for random forest. Fit a random forest regressor on the training fingerprints, read its feature importances attribute, and sort to pull out the 20 most important ECFP bits. Because the features here are fingerprint bits rather than named descriptors, the interpretability step is mapping each top bit back to the substructure that switched it on. Example 22 performs cross-validation and hyperparameter tuning. Define a grid over the number of trees, max depth, min samples split, and min samples leaf, then run grid search CV with 5 folds scoring on R² to find the best combination. Refit with those settings and use the cross-validation scoring helper again to report mean absolute error as a mean plus or minus a standard deviation across folds. If test performance is much lower than cross-validation, you may have data leakage or distribution shift issues. Example 23 compares multiple models systematically. Create a dictionary of 5 models: random forest, gradient boosting, SVR with an RBF kernel, ridge, and lasso. Loop through them, scale the features for the ones that need it, train each, and evaluate on the test set. Record training R², test mean absolute error, training time, and the overfit gap between train and test R². Plot results as a bar chart. This helps you select the best model for your specific dataset. Now let's implement ADMET prediction models. This chapter's ADMET examples are 24 through 27. CACO2 permeability for intestinal absorption, HERG inhibition risk for cardiotoxicity, blood-brain barrier permeability, and a comprehensive drug likeness evaluation that pulls the others together. All of them are built from physicochemical descriptors you already know: molecular weight, log-P, TPSA, and hydrogen bond counts. Why this matters? About 40% of drugs have low water solubility, which can impair oral absorption, so a potent compound is not yet a usable one. Before those models, a word on log-P, the partition coefficient that measures lipophilicity. You don't need to train anything for it. RDKit estimates log-P straight from structure with descriptors. Mol log-P, the Crippen method you already used back in example 3, and it is one of the 4 criteria in the Lipinski check in example 4. Log-P runs through everything in this section. Too low and a compound won't cross membranes. Too high and both solubility and cardiotoxicity risk get worse, which is why it feeds every ADMET model here as an input feature. Example 24 tackles CACO-2 permeability prediction for intestinal absorption. This is a classification task, high permeability versus low, with the boundary around a p-ap of 10 to the -6 centimeters per second. Calculate 10 ADME descriptors per compound molecular weight, log P, TPSA, hydrogen bond donors and acceptors, rotatable bonds, aromatic rings, fraction of sp3 carbons, molar refractivity, and heteroatom count. Then fit a random forest classifier. Be honest about the scale here. The worked example runs on only 10 compounds and reports an illustrative ROC-AUC of 0.75. Practical work needs at least 500 compounds with experimental CACO-2 data and an external validation set. Example 25 assesses hERG inhibition risk for cardiotoxicity. This is crucial. hERG blockers can cause fatal arrhythmia. The example is deliberately simple. A rule-based risk score out of 100 that adds 30 points for log P above 3, 25 for molecular weight above 400, 25 for a basic nitrogen, and 20 for 3 or more aromatic rings. 70 or above is high risk, 40 or above is medium, anything lower is low. Terfenadine, a known hERG blocker, scores 80, aspirin and caffeine score 0. For accurate prediction, you would move to machine learning models trained on ch-EMBL hERG data and confirm with patch clamp assays. Now let's explore graph neural networks. Example 28 shows molecular graph representation. Convert a molecule to node features, including atom types and hybridization, and edge features, including bond types. Create adjacency matrix from bond connections. This representation captures molecular topology directly. Example 29 implements a simple message passing network from scratch in NumPy to make the mechanism visible. Each layer aggregates information from neighboring atoms, then updates every atom with its own features plus that aggregate, and you repeat this over 3 layers. A readout step pools the node features into one molecule-level vector for prediction. Note that this one is untrained and educational. The weights are random, so treat it as a diagram you can run, not a working model. Example 30 moves to a real library, PyTorch Geometric, as a conceptual skeleton rather than runnable code. The model class stacks 3 GCNconv layers, applies global mean pooling to collapse atoms into one molecular vector, and finishes with 2 fully connected layers. Molecules are converted into the library's data objects, carrying node features and an edge index. On when to reach for this. GNNs typically outperform traditional methods on larger datasets, especially beyond 10,000 compounds, while on a few thousand, a tuned random forest on fingerprints often matches them for far less computation. The chapter closes with a separate project challenge, set after the 30 examples rather than being one of them. Predict COVID-19 protease inhibitors. Download activity data for the SARS-CoV-2 main protease, also written 3CL protease, from ch-EMBL, target CHEMB L3927. This is a PIC50 regression task, and the project sets a target for each of 3 models. Test R² of at least 0.70 for random forest, 0.72 for the neural network, and 0.75 for the GNN. This applies everything you've learned. The project challenge workflow has 5 stages. Stage 1, data collection. Pull main protease activity data from ch-EMBL with p-ch-EMBL value greater than or equal to 5. Aiming for 500 or more compounds, note you take the p-ch-EMBL value directly. There's no conversion step. Stage 2, preprocessing. Remove duplicates and invalid SMILES, apply a Lipinski filter, strip outliers with the interquartile range rule, and split 80-20. Stage 3, model construction. Build and compare 3 regression models, random forest on ECFP4 fingerprints, Akira's neural network on RDKit descriptors, and a 3-layer GCN against their R² targets. Stage 4 ADMET evaluation of the top 10 predicted compounds. Lipinski, HERG risk, CACO2, and blood-brain barrier, combined into an overall score. Stage 5 hit selection. Keep compounds with predicted PIC50 of 8.5 or above, an ADMET score of 60 or better, and at most one Lipinski violation, narrowing to 3 to 5 final candidates. Let's review what you've learned in this hands-on chapter. RD-Kit fundamentals. SMILES parsing, visualization, descriptors, fingerprints, similarity, substructure search, three-dimensional generation, and file IO/CH-EMBL integration. Target search, activity retrieval, data preprocessing. QSAR modeling. Train test split, random forest, SVM, neural networks, feature importance, cross-validation. ADMET prediction for key properties. An introduction to graph neural networks. Best practices for drug discovery, MI, include: always validate SMILES before processing, use cross-validation for robust model evaluation, check applicability domain for predictions, document your preprocessing steps for reproducibility, and version control your code and data. These practices ensure your models are reliable and reproducible. This concludes Chapter 3. You now have practical Python skills for drug discovery MI. You can process molecular data with RD-Kit, access CH-EMBL bioactivity database, build and evaluate QSAR models, predict ADMET properties, and understand graph neural networks. In Chapter 4, we'll examine real-world case studies from successful AI drug discovery companies like Exscientia and In Silico Medicine.